So I'm going to try this again. If you were watching, I started this and then I'd realized that I don't like the aspect ratio, or I didn't like the aspect ratio. I don't think it works very well. Here, I'm gonna make this a little bit smaller, put it down here in the corner because nobody really needs to see me. What you really need to be able to see are the slides. So in this morning's lecture, I actually ran out of time because I spent a lot of time talking through the networking section, and I said, well, I'll do the rest of it, the end of it on the next lecture. And then I thought about it afterwards and I said, the problem with that approach is the next lecture is really important because it's actually about ordering of events and about what it means to say something happened at a particular time. Because as we start to move into larger scale distributed systems, causality, ordering become much more difficult for us to ascertain. That is, in fact, why there is an entire course on this, because it's really hard to wrap your head around that. The networking stuff, on the other hand, is a review, and I'd rather not spend too much time on the review. So I said, you know what? I need to actually come back, and I need to to do a better job of this. And Uh, so I want to give you guys the review. So I'm going to start where I started before, which was the network functionality section. And then I'm going to um, move on to, I'll move through the content there. And that way, when I'm back giving the lecture on Tuesday, you won't have to, we won't have to spend time because I realize there's still a fair amount of content here. I think that the content is a little bit lighter because it's sort of the opposite of my usual style. Because I mentioned I borrowed these slides. I use slides that Ivan Bestraznik had used in his previous presentation here because he's an excellent instructor. It was a great course. Students really liked it. I know that Ivan has a better sense of what people know about networking than I do because, as I mentioned earlier, I grew up with this networking and I learned a lot of it by doing things and absorbing them as they arose rather than trying to pack it into a 90-minute talk. So so let's see. What is, oh, I have to figure out where the screen is. That's the problem. So what I did was I have these large wide area screens, and one of the options they have is they can actually split the screen into two subscreens. And so I split it into the second subscreen here, specifically because it's easier for me. Let's see. Wow, this moved. Nope, that's it. Okay, so here. No, it didn't move. It went back through the slides that I had told it to skip. So let's try this again. Computers, they'll be the death of me, I swear. Okay, so there, this is the network functionality. So I'm using a smaller screen because that then allows me to, you to actually see this without getting big sidebars and whatnot, because a 32 by 9 format screen, I think it's 5100 by 1440, is it, it's not going to give you a very good impression. You're not going to be able to see the slides. So here we are. So we're going to talk about network functionality, and I'm going to dive down into this in a little bit greater detail. There we go. And the first place to start is in layering. And I mentioned layering before. This is a technique that we use where we build modules that we can then plug together. And we don't do that because modular software is, I don't know, somehow more efficient, because in fact, it's exactly the opposite. What we're doing is we're giving up some level of efficiency, because if I build completely optimized bottom to top stacks for one particular task, you can't beat that as you begin to introduce generality. But the flip side is I have to build it all. This is why we really only have like just a handful of operating systems to choose from rather than tens of thousands of them. As we move up, the cost of optimizing for a particular use case goes down, and the benefit continues to stay the same, or at least improve a degree, maybe slightly. So we can build general purpose lower levels and then build special purpose higher levels. At the top of that stack, we have the application. Applications are purpose built. I'm sitting here using OBS Studio. I was using OBS Studio earlier in the day when I was at the lecture hall there at UBC. Now I'm sitting at home, and since I don't want you to see the messy room behind me, I've picked some generic background image, and the computer's doing its thing and making the messy room go away and giving me a palm tree instead. Applications very seldom work in a vacuum. I'm running OBS Studio. OBS Studio, in turn, looks very similar to me on the computer here compared to the computer, my laptop that I was using when I was at UBC. So the functionality is the same. The application is similar, but in fact, I'm using a different computer. I've got different display devices. I'm using a different camera. I'm wearing a headset this time instead of trying to use the wireless microphone that I used when I was there in the lecture hall. But in the lecture hall, I don't want to be sitting here with a headset on because I have to interact with the humans in the room. So it's slightly different circumstance. Same application. That's my point. Applications typically don't run in vacuums. They don't run without working with other applications. So we actually even further subdivide functionality in an application. Then we end up with applications talking to other applications. That's great. I'm running this on my desktop computer with OBS Studio. So the same software, but completely different hardware, completely different functionality. And yet it's taking that and it's streaming it through Twitch. And it's recording a copy of it on my local computer, which I can then upload to YouTube. There you go. And now that, of course, is where that host-to-host connectivity comes into play, because talking to Twitch, talking to YouTube, those are over the internet. Those are things that are not hosted on my local computer. So now we have the network starting to play a role there. Now, of course, beneath that higher level network functionality is all this lower level network functionality. I have an Ethernet connection that plugs into my wall that then goes to my router, and my router then talks to my ISP, and my ISP talks to other ISPs, and then eventually those packets flow to wherever they need to. And I have a combination, even in my apartment. I have both fiber, because there's a fiber optic cable that comes directly into my wiring closet, and then I have copper from that point over to my to the jack where I plug my computer in. So the benefit of layering is that it provides us with some level of modularity and abstraction. We have applications talking at some peer layer. They don't have to be the same application. They have to agree on a functional interface, like, talking to Twitch, doing dynamic streaming like that. Or with YouTube, it's uploading a video, and then YouTube does a whole bunch of work to that video. But I have an interface, and I can exploit that functionality through that interface. That's what happens at the application layer in the network stack. Below that, then I have other things. This kind of ignores the fact that there are session and presentation layers also within this, because at least in the TCP model, we don't really distinguish between those different pieces of applications. In the OSI model that I spent more time talking about earlier, we break that out. And even in the TCP model, when I have an application, there are still libraries and there are still other applications that are providing me with some of that functionality about session management and so on and so forth. So the concept isn't different. The implementation, it's not even the implementation. It's actually just the way we describe it. We sort of lump session and presentation together with application in this picture. Fine. Doesn't change our analysis. Transport. I'm running probably TCP. That's the most likely transport for me to be using. And TCP will in turn then be running on top of IP, which will then be running over the Ethernet connection, which will go to the wiring closet, where my router will convert an Ethernet frame into a whatever the framing protocol is for the fiber optic cable that's in the wiring closet. And then that fiber optic cable will talk to some other device that will then transmit it over some other network connection. And then eventually it will come out the other end into a data center, probably someplace in Seattle, just a guess, since Twitch is an Amazon company. And then it will find its way to one of the stacks there, where the network protocol will deliver that to a particular machine in a rack, and that rack will then read the data off that and deliver it to some application, some service that is there waiting for my streaming data. And then they're going to turn around and they're going to deliver it to you. The benefit of layering is that it allows us to reason about what we have to do at each individual layer. There's no question building it from bottom to top with optimized paths is fastest for that use case, but it's not generalized and it's actually very fragile because it's hard for me to fix and change things. The larger the piece of software is, the more specialized it becomes, the more it's tied to hardware, the more difficult it is for me to broaden it, to add features, to build new pieces of software, because if I always do it with silos, it's always going to be a lot of work to do that. So it's a trade-off here. And our trade-off here is that we try to do this so we can reason about things. We try to enable ourselves to build better and more efficient software, or faster at least. We can improve the individual pieces of that stack. And as long as we obey the guarantees of the actual interface, then the reasoning that someone above that did doesn't break. So that's a compatibility, in fact. So when I build a new stack, I build a new TCP implementation, I literally have to focus on making sure it interoperates with other TCP implementations. If it doesn't, then it's useless. Building software that talks to other software I build is not that challenging. Building software that talks to other software that other people build is a lot more challenging. It means we really have to have an agreement. One of the motivations behind Alternate Path 2 is is helping you understand that in a pragmatic sort of way. I build a service, you build a client, and then somebody else comes along and says, are you actually obeying the specification? Now, ideally, what I probably should have done is I should have said, you build a service to a spec, and you don't get to see what the application does. The application builds a service to that spec, and they don't get to see what the service does. And then we plug them together, and we see what happens, and we see how good you are at conforming. But there's probably not enough time to do that. That is the way it works in the real world, however. We spend a lot of time trying to figure out why things aren't working together because one person wrote it one way, one person wrote it the other way. Oh, you mean that the capitalization of the characters isn't allowed in the protocol specification? Probably not. Sometimes, I mean, there's this old adage in building protocols that says be liberal in what you accept and conservative in what you send. And the idea is that if you let other people be sloppy, then that'll work out fine. But you should always be strictly conforming as much as possible. And the idea is that we want interoperability over enforcing conformance. My job as an implementation is not to enforce the conformance of other people's implementations. And as long as I'm implementing the spec, that's great. Okay, so by using this sort of interface model, we focus on the interface definition and we get to abstract away from the implementation. That sounds great in practice. In the real world, what often happens is that we still end up having some issues related to the implementation, and we just have to figure them out, work them out. And over time, we learn what matters and how to make that happen. Okay, so all of this is based on protocols. Protocols are really fundamental for any kind of communications, whether it's computer communications or human communications. What it does is it defines how we talk to each other. I used the example before. If someone calls you on the phone and you answer it, I don't know about you, but I really don't answer the phone very much anymore, unless it's from a number I recognize. And somebody starts speaking in a language I don't understand, I just hang up. That's because I don't know the protocol. I don't know what they're talking about, and therefore I can't process any of the information they're giving me. So that's why having a protocol is really important here. So what do? We define what the interface is to the higher levels. That's part of our interface protocol. And then how we interact with peers. Now, when it's across a network, this becomes some sort of communications exchange. Hi, hello. So I took this diagram from Ivan because it does actually capture this. You walk up to someone and they ask you, you say, hello, how can I help you? Um, and they say something you don't really understand, in this particular case, you ask them a question. You go, okay, well, I'm not sure. Where are you going? So clearly, this is some sort of a flight sort of related thing, presumably. Or maybe you're taking a boat. I don't know. Maybe you're driving a car. Whatever. It doesn't matter. So in order for us to successfully communicate between peers, we have to understand, how do I initiate communications? What is the format of the messages that I'm sending? It turns out that some computer systems store data in memory in um, different byte orders. Well, that's fine as long as you're only sending single byte characters, because there's no issue there. But when you start doing multi-byte characters, you have to worry about, is the most significant bit at the bottom or at the top? And there are reasons that people choose these things. It is a well understood issue. We know about it and we deal with it. That is a presentation layer issue. That is, in fact, exactly what presentation is about. Do I use little Indian order? Do I use big Indian order? There's actually even a weird Indian order that was derived from the PDP-11. We don't really need to talk about it. Most of the time, you probably won't actually even think about it. You start using packet sniffers, though, to look at the network, you will see it. You will have to recognize that things on the network are sent in um, in some sort of presentation format. If you look at the way that the original Sun RPC worked, ONC RPC, it always used what's called network byte order, which means uh, most significant byte first. So it's most to least. And then if you look at the way that DCE RPC works, uh, which is what Microsoft uses, and that lots of interesting historical reasons for that. But that's why what Microsoft uses for their RPC. And you'll find that in the real world, both RPCs are used. In DCE RPC, they instead said, we're going to indicate as part of our header what the byte order was of the original sender. And then the recipient is responsible for putting it in the byte order that's needed by that computer. And the rationale for this was that in ONCRPC, they always put it in network byte order. So if you're running from an Intel machine, which is a little Indian machine, and you're talking to another Intel machine, which is also a little Indian machine, then what you're doing is you're byte swapping on one end, sending it across the network, and byte swapping it back on the other. So you're doing unnecessary data conversion, and that slows things down. If you can say, here's the format that I used, the other side can then say, oh, okay, I can adapt to that. I can handle that. I mentioned this in the lecture earlier, which was about the ordering of messages. This is going to become a big issue. What is the order that messages were sent in? Because the network that I'm using may not necessarily guarantee ordering. And if it doesn't guarantee ordering, then I have to build something in the system at my layer that guarantees that, if it is a service guarantee I'm providing to the layer above me. If I'm UDP, I am going to guarantee the order the data is delivered in. That's one of the very few guarantees that UDP actually provides. UDP doesn't actually even allow you to do large messages, though. It has a finite limit, I think it's 64K, on the size of a UDP chunk. And that's because they didn't want to spend more than 16 bits to describe an offset into the stream. And that's fine. That was a decision they made when they built that particular protocol. It doesn't make the decision right or wrong. It is just the way it works. And if you're going to use that protocol for delivering your own services, lots of RPCs, for example, sit on top of UDP and implement functionality on top of UDP, which includes the ability to send things that are larger than 64K. They deal with things like the data presentation orders, so on and so forth. And so lots of different options there. Again, it depends upon what you said was going to happen at that particular interface. Mapping a message to what it's supposed to do is another thing that you actually have to deal with at each individual layer within the protocol stack. Some of this ties into what I was just talking about. Like if I actually have to take a big message, let's say I take a 64K message on UDP, and I divide it into smaller chunks so I can put it on top of IP, then an IP then goes over some network where the chunk that I sent, let's say I decide I'm going to use 4K jumbograms. And the term jumbogram isn't one that I coined. It was one that people realized when they figured out that they could actually send oversized Ethernet frames. So great. So you can send 4K. If it's on the same subnet, then everybody can get it as long as any hardware along the path handles these oversized packets. But if you run across a network that doesn't do that, then what happens is you have to break it up. And that can happen at the IP level, where literally you might go over a packet radio, which has 400 and some odd byte limit, if I remember correctly. And it's one of those places where we use that as the extreme example. Maybe it's 256 bytes, but it's really small. And it's an extreme example, but it's good to use because it makes us think about what's the worst case there. So IP gets a 1500 byte Ethernet packet and says, I have to break this up into smaller pieces. And so it breaks it up into smaller pieces. And then when it gets delivered to the other end, it shows up and the transport protocol IP will do reassembly. It'll actually, because it had to make them smaller, it will have to reassemble it, and then it will give it back to the next layer up. Because the next layer up doesn't know what happened. It's not supposed to know what happened. If IP had to fragment the packets into smaller buffers, the TCP layer should not know that. Now, of course, again, there's that efficiency thing. If TCP knows that the maximum transmission unit is small, then it can scale things back and it can say, okay, well, I won't send it to be any larger than this. And um, that actually makes things more efficient because now IP doesn't have to do its own fragmentation and reassembly. What do we do with those messages? Well, since, in the case where I segmented something, those messages tell me how to put the message that I need to give to the next layer up back together. So that's part of that action mapping. When this gets up to the HTTP layer, it's going to be a get or a put, for example. And that's going to tell me at the protocol level what I'm expected to do with this. Error handling. Things go wrong. Once we have semi independent entities, stuff breaks. You're talking to service, the service goes away, the network goes away, your client goes away. How do the other pieces of the system have to handle that? And ideally what we do is we define, here's how you handle it, here's what you do. That will depend on the protocol. In the case of TCP, it says, sorry, connection's gone. UDP has no state. It doesn't have connections. So as far as UDP is concerned, it doesn't know what's going on. So some higher level is supposed to handle that, like an RPC level. When you look at the network file system protocol, it has a model where the server goes away and it just keeps retrying things and it keeps retrying them. And it has variations on that. I don't want to get into it, but it has a different model than what UDP provides, which is, I don't know, I sent the datagram. It's best effort. If it got there, great. If it didn't, not my problem. How do you deal with termination of the connection? In TCP, you actually have to negotiate when to disconnect. This is interesting because a different class that I teach, the project is building essentially a dumbed down web server, and students walk in and they automatically assume that when the client is done, the client should just, the server should just, oh, sorry. So the client sends a request, the server sends a response, and when the server's done, it should just disconnect. But and when we first started building HTTP servers, 0.9, that's what we did. We said, okay, you get your answer. But then we found that if the client needed more information, setting up another connection could often be the dominant cost associated. Because maybe I'm only fetching a 30 byte blob. And that happens a lot with web pages. I'm fetching small different pieces from lots of different places. But maybe I'm fetching 16 different things from one place. Well, why would I want to disconnect after each one of these little objects gets fetched? So instead, they changed it in HTTP 1.1. The server doesn't immediately disconnect. The server still has the right to disconnect, but it doesn't have the obligation to disconnect. So a client that was built in 0.9 and assumes the server will disconnect when it's done, and rather than keeping track of how much data has the server sent me, it doesn't work. So it's important to understand what it means when we say we're gonna terminate the connection, and we have to have an agreement there. That's why protocols are important. In IP, part of the point of this layering is that we can actually have things floating back and forth between the layers uh, from one into the other. So in the example here, we have a message that goes from the application layer to the transport layer, then through the network layer, data link layer, physical layer, and then, oh, it might go through a switch on my local network. Okay, that's fine. And then it might go through a router or gateway. So for example, that bridge switch could be a wireless access point. The wireless access point might in turn be talking to an actual router that protects you because you can't trust people outside. And it will then send that up through a stack that is not a full stack. Notice it only goes up to either the data link layer if it's a bridge or a switch, or it goes up to the IP layer, the network layer, if it's a router or gateway, and then it sends it back out to the next link. This literally is nothing more than just message passing, handing the baton off from one machine to the next machine to the next machine to the next machine until we finally deliver it to the recipient, the application or service on the other computer. I mean, this says host on both ends because it doesn't actually matter. If this is a peer-to-peer connection, we go through the same exact process. All right, in the IP protocol suite, most everything comes through IP. IP is a very general purpose service. We rely very heavily on it. It is heavily optimized. It is pretty simple. And that's going to be an important principle. Keep it simple. We specialize at the top. We can specialize at the top and the bottom, but this area in the middle is where we really don't specialize very much. There are other network protocols besides IP, but they're not very frequently used these days. And that's because we found that IP was sufficient to get almost everything done. It balances generality and efficiency quite well. Each layer builds messages that are a composition of pieces from the layer below. The interesting thing about this picture is that it implies there are only headers, but I will actually note that it is very frequent that there are both headers and trailers, or footers, if you want to call them that. And it doesn't make any difference. So the point here is when the application builds a message, it does a send on like a in an application program using the BSD sockets API. So it does a send, and the send then gets down into the TCP layer, which puts a TCP header, and TCP has trailers, which is why I mentioned it. So TCP header trailer. So we frame the message above. You'll notice that the message that started at the top is still there. Then the layer below that adds its own header and footer, and then the layer below that does what it needs to do, header, footer, sends it across the physical layer. And then as we go back up the stack, what's happening is that layer is consuming the header and footer that it attached to the message and delivering the message to the layer above it. I know I've said this before, and I will point it out again. This is an awful lot of data copying if you do it wrong. And data copying is really expensive. Network stacks are highly optimized to do this in a way that doesn't copy the data typically. Worst case, you can always copy the data. But often what ends up actually happening is you end up with either a logical or a physical description of this packet. If I have a logical description, what will happen is I'll end up with a series of data structures, each of which describes that layer's little piece of the entire packet. And when it gets down to the network card, what we'll hand to the network card is a list of address length pairs that correspond to that message. And that way we don't actually have to do data copy. Instead, what we're doing is we're building a chain that describes a logical buffer, even if it's not physically in the same chunk of memory. And network cards do this quite well. It's a feature of the hardware. Different implementations of the same interface at the same layer are supposed to be interoperable. There's information at each layer that provides us with what we actually need in order to deliver the messages of the next higher level given the service and the interface that we have guaranteed. So it also allows us then to multiplex. So I can have lots of different TCP connections on top of the same IP network. I don't need one IP network per. I can have multiple different services on top of the same TCP connection. I can, it's kind of like I can have multiple web servers, believe it or not, multiple web servers on port 80. So the TCP differentiator is the port address, but then it goes to the same web server who then looks at the URL that was actually used to access the website. So now it distinguishes and it demultiplexes based upon the host name rather than on the port. And you can keep doing this iteratively at each layer. IP is heavily multiplexed. Here is a partial list of IP protocols. It is not an exhaustive list. There are quite a few. You'd be surprised when you actually start looking at how many there actually are. Um, I know from personal experience it's not there, but I think I mentioned I actually worked on a transport protocol when I worked for David Sheraton called VMTP, and it was an experimental protocol that combined the functionality of TCP and UDP in a single protocol, and it has its own IP protocol number. So it was interesting because it also took advantage of IP multicast to do one-to-many discussions. And it was fun because we used that functionality to build a version of Maze Wars that ran over an internet. We didn't run it over the internet, but we ran it across subnets. And it was noticeable how much better the performance became when we started using IP multicast, because you could have multiple players, but we would only be sending one packet. And that was a lot less load on the very less capable computers that we had in the 1980s. So protocol demultiplexing is implemented by using information in those headers. For example, TCP has a port number, IP has a protocol field, the network, the data link layer has a type, so that way we know what network protocol is inside that individual data link frame. IP is the predominant one, but you can still see other protocols within that. So the goals when we were designing internet protocols are: we want to connect existing networks. We need to make sure that they are failure resistant, that they can survive transient problems. You don't want everything to collapse just because there's something that goes wrong. One network connection goes down. You need to be resilient in the face of that. We want heterogeneity. Now, there are lots of reasons why heterogeneity is desirable, but the reality is we have heterogeneous networks, we have heterogeneous environments. We need to have, it would be a really bad world if our Windows boxes and our Linux boxes couldn't talk to each other. It would significantly degrade the functionality that we've come to expect from them. We expect distributed control. What that really means is we've got different people who own different parts of the internet, and they each get to manage their little piece, but it all has to work together. So we do have to cooperate, and that means we need to agree on how things work. So for example, the way that we set up routing in the broader internet with the border gateway protocol and boundary gateway protocol, and the autonomous systems and the way that they're numbered and how we deal with routing and whatnot. It requires some degree of cooperation, and this is going to be really challenging because the moment that we start trusting outsiders, third-party entities, we run the risk of running into problems. The network needs to be very easy to use. We have to be able to quickly and easily attach to it and get it just running. We spend a lot of time doing things like the dynamic host configuration protocol, DHCP. We want it to be as cost effective as possible, which I think Ivan actually used cost effective and I said cheap. Right, we want it as cheap as we can get it. That's really what drives this. as long as it provides the functionality that we require. We want economic accountability. We need to be able to bill people for their use. In all fairness, most internet usage is actually so inexpensive that we just simply use a flat rate model rather than try to account for individual packets. It's quite surprising when you look at metered services, for example, the electric market. About a third of the total cost of electricity is just the cost to account for it, to meter it, to say, okay, well, this is how much we think this is how much you are using because we're measuring it, rather than just simply saying, well, you know what, everybody's just going to have to contribute X or based on some other external factor, and that's just the reality. But in the network, in fact, the cost of delivering a single packet is so low that it isn't cost effective for us to try and track it that way. People have done it, and it almost never is worth the extra effort. There are going to be cases where it is worth the extra effort because there's some significant amount of resources involved in that. If you try to use your Wi-Fi on the airplane, they're going to charge you for it, and that's because there's a lot of expensive infrastructure that goes into that, and they're trying to recover those costs. Although it's getting cheaper and cheaper, and now some of the airlines are starting to give it away for free. So you can see what happens. You start with a metered service, you can end up moving to a flat rate service or a service that's so inexpensive that the people providing it just simply add it into their overall cost. A recommended reading here is End-to-End Arguments in Systems Design. It is Jerome Seltzer and his compatriots. It's a very interesting piece of work. Seltzer is a very interesting writer of that time period. I have spent time looking at some of the things that he's written about naming because I'm very concerned about being able to find things. And the first place you start is you say, well, we name files, so isn't that enough? And even when he was writing, he said, no, this is a good place to start, but it's not enough. Survivability is a really big issue in the network because network disruptions occur. Individual routers might fail. We recover from that because we can pick a new route. There's lots of different ways for me, for example, to get from here to UBC campus. There are many different ways that I can do it. What I mostly do is I try to choose the one that's most efficient. So I look, are the buses running? Yes, the buses are running. What is the optimal bus for me to take? Well, for me, it's the 44. So I take the 44 to UBC, but that will depend upon the time of day, and it will depend upon whether or not the 44 is running, because it doesn't always run. Doesn't run on weekends, for instance, and various factors. I have real-time data. That's very much like a routing table. That's very much like routing state that is used in the internet. It says, here's the fastest way for the things that have just recently gone through the network. It doesn't tell me what it's going to be for me, but the best information I can get is what was it like for somebody just before me. But let's say the 44 gets canceled because the driver is out sick. Well, if I go stand and wait for a 44, I'm going to have to wait until the next one. So that means that it's going to take a lot longer. If I look and I go, well, the 44 is not running because it snowed. Well, now I have to say, oh, okay, well, I know from personal experience it takes about 2.5 to 3 hours to walk to UBC in the snow. So I would have to plan accordingly. Have an 8 a.m. class means I have to be out the door by 5 a.m. if I want to make sure that I am there in order to teach. That's a worst case analysis because I have enough experience to know that that's what it's going to take for me to trudge all the way through the snow. Now, whether I'm going to do that or not is a different matter. What happens if I figure this out at 5:10? Well, is it worth me spending 3 hours to get there and be late and find out that nobody else showed up? I don't know. Hopefully that won't happen. Hopefully I won't have to trudge through the snow for 3 hours to teach to an empty classroom. And some of this depends. So in this analysis, what we're talking about is where do we keep the state? So state that's in the network, we often replicate things. Routing tables are replicated. They exist in whole or in part across lots of different nodes. So the failure of a single node doesn't actually break On the other hand, state in the host goes back to this idea of fate sharing. If I have multiple processes in the same host and they're talking to each other across a TCP connection, they both die together. If the machine crashes, they both die. But an application could crash, but not the other one. So it doesn't really look any different than if a remote machine crashed. I would just stop hearing from the other side. Eventually, I will have to figure that out. So we use timeouts. We need to figure out how we're going to recover from that. In all fairness, engineering uh, robust survivability in the internet is really hard. We have lots of protocols around detecting various state conditions. We have decades of experience in finding out all the things that can go wrong. And we don't have infinite resources. We can't do an infinite amount of buffering. So eventually we're going to run into a time when we can't send packets. And so we have to decide, which packets do I throw away? Do I throw away the packet that just arrived, or do I throw away the package at the front that is oldest because it's at the front of the queue? Probably haven't even thought about those kinds of failures and how we deal with them. On the other hand, state in the host is a lot simpler because it's just in memory. It doesn't affect anybody else. And my failure because something went wrong on the host generally isn't going to affect other people. Hand wave, hand wave, hand wave. The network has to maintain the routing state. The host doesn't need to maintain the routing state. If the host needs to know what the right route is, well, the host shouldn't be routing in the first place. It should be using naming to use appropriate delivery of the messages to whatever piece of the lower layer needs that information. I don't trust the network. There's a whole trust model there. I don't trust the network, but I do trust the host. I don't completely trust the host. I trust my host. The software I wrote is clearly not broken. It always works right. I don't trust your host. So, all right. I'm going to highlight fate sharing here again because and I'm going to point out that there are subtle gradations here. Fate sharing makes things a lot easier to reason about. If we know that two things are going to fail together or not fail, then that's fine. We can handle that. This idea of fate sharing is one that we are going to be using over and over again because it's really important when it comes to um, dealing with failure. So in our mythical internetwork state, we have the connection, which has state, the recipient that has state, but we don't actually have any connection state in the middle. These are datagram services. IP is a datagram protocol, so it doesn't actually, ignoring certain esoteric features, it doesn't actually have end-to-end connection state. And the certain exception is the one I mentioned briefly, which is IPsec kind of screws around with these things a little bit. And again, it reinforces the idea that when we start building these models, we start with very simple models. And then as we find reasons to make the models more complicated, to violate our own constraints or our own rules, then we have to go back and we have to justify that and say, well, performance is more important here. And this is what we're going to do. And you actually see that in the Salzer paper. Definitely see that. They talk about how these are principles of good design. You start with simple and you try to minimize the addition of complexity until it's actually warranted by the situation. Um, so we only want to lose state if the entity is lost. TCP state gets lost if a host crashes. But if a relay crashes, there's no TCP state in the relays. So the fact that a router crashed, we don't care. TCP will retransmit messages, and eventually the network will start routing our packets over a different path, and TCP will recover. TCP is quite amazing that way. I think I mentioned this before. As I recall, and I didn't go down and grab a citation for this, but as I recall, TCP is known to be able to make forward progress in the presence of 90% packet loss, which is staggering. But that has its own disadvantages because now it creates slowdowns rather than failures. So there's a lot of trade-offs involved here. I'm not going to drill down too much into that. But as I said, in the real world, we end up being very flexible about what some of these things mean because we often end up balancing knowledge and control in ways that we try to preserve as much of that resiliency as we can, but we don't do it to the extent where it sacrifices performance. I mentioned bonding. So I can multiplex multiple different services over a single link, and that's what basically the internet does. So you have, I have a 1 gigabit link to my router in the closet. It has a 1 gigabit connection to TELUS. TELUS then somewhere is going to be scaling that up. It's not going to have 1 gigabit connections. It's going to have 10 gigabit connections or 100 gigabit connections. At the present time, last I checked, the fastest single link network speed was 400 gigabits, um, which is super fast, very expensive because it is super fast. And I'm pretty sure I was reading that people were working on 800. So we will see terabit uh, networking connections. But you probably don't need a terabit network connection at home. If you are an ISP, on the other hand, you will want to use much faster connections and you're going to multiplex traffic on top of them. On the flip side, suppose that you live in the boonies and the best you can get is a T1 line, 1.544 megabits per second. Well, you say, okay, been there, done that. Maybe I can take two of them and I can bond them. So I can use a protocol that can send frames across either one. And on the other side, there will be another protocol that knows that those frames need to be pulled off of the separate connections and then merged as if they came from the same connection. Bonding. Load balancing is another common one. So I might have two internet connections to two different ISPs because I'm worried about one of them failing. But in the norm, what I really want to do is I just want to like round robin back and forth until I detect that one of them seems to be experiencing high failure rates. And if I notice that one of them is experiencing high failure rates, then I'm going to say, I think this might be dead. At which point, then I switch all the traffic to the one that's working. Well, how do I do that if I don't look inside of the packets? I mean, if I'm really sitting at the IP level, and so I don't know anything about the packets themselves, how will I know when the protocols above me are not working the way they're intended? So what we find is that, in fact, gateways often do deep packet inspection, where they don't implement the full protocol, but what they do is they look inside of the messages, the packets, to say, what does the TCP state information tell me? Oh, look, this is a retransmit. Oh, look, I can see that there is a problem, that TCP is retransmitting and it's not getting answers back to these things. So maybe that link is broken. We do intrusion detection systems, which do pretty much the same thing, which is they do deep packet inspection to look for malicious behavior, malicious actors. We do that for security. It totally violates all the layering and all the stuff we're talking about here. But the reality check is security turns out to be more important than trying to stick to some abstract definition of purity of interface design. Routing is often a little more complicated. Well, the protocols are insanely complicated. So I'm going to leave that one just to say, yeah, routing, we have, um, we don't, we tend to violate um, some of the boundary crossing issues. We violate some of the boundary restrictions there because we need to understand like a network that has multiple ASs. We need to understand a little bit about the topology to be able to make intelligent routing decisions so we don't end up killing someone's network. And those are baked into the protocols. They build them in there. But it's taken years, decades to build these things because we are basically violating our own layering. Security and encryption can be really complicated, and they definitely can end up causing problems across boundaries. Uh, SSL for an HTTP connection, so you have HTTPS, is a high level implementation of that. And in general, that should be fine. But then there are things that we have to keep in mind there because we are multiplexing potentially uh, multiple different security domains on top of a single SSL connection. Lots of fun, interesting issues around that. Again, flow control often requires that we understand the protocol and we understand the network and the topology of the network and what's going on there. One of the reasons that we've seen a shift away from TCP and towards UDP for some things, like the HTTP 3 protocol, which is based on Google's Quick work, runs over UDP rather than TCP. And some of it is because the TCP flow control has become so expensive and so constraining that what we're finding is it's better just to not use TCP at all and just simply rely on not using the TCP guarantees. Fragmentation is like I already mentioned that one case where in fact TCP will ask, yo, what is the largest MTU on this particular path so I can build packets that won't need to be segmented and reassembled by IP. Makes sense. It's a good thing to do because it improves performance. So here's a design question for you to consider. Where do you implement reliability? Do you do it in the network or do you do it on the endpoints? So we could do it in the network where we guarantee that any packet that arrives in a switch will be delivered to the next switch. Or we can do it at the endpoints. Well, that sounds like a simple question, doesn't it? Yeah, it sounds simple, but it turns out it's actually a little more complicated. So in a hop by hop option, how do you guarantee delivery? If the relay switch actually reboots, how are you going to do that? Well, I mean, if it's in DRAM, it's going to get lost. The DRAM contents aren't saved. I could save all these packets, but my gosh, what am I going to do? Write them to NVMe? Obviously, I'm not going to write them anything slower than that. I don't even want to write them to NVMe. Um, there's persistent memory now. Well, there was until we withdrew it from the market. But what are the costs associated with that? And so, in fact, what you usually end up doing is concluding that it's too expensive to provide this kind of reliability for an infrequent event. And this is a very important engineering observation that comes up, and that is do not optimize the uncommon case at the expense of the common case. The common case here is nothing goes wrong. And this is going to bite us over and over again because now we're talking about how we're going to deal with all these failures. How are we going to do that efficiently without penalizing the common case? I'm willing to pay a little bit for it, but not a lot. Queuing theory bites you here too. There's been a huge amount of work in building routers and switches and buffering. And so the naive thing is you say, well, just make the buffers bigger. Turns out that can cause more problems than it solves. You end up with head of line blocking. You end up with because the connection's broken, and so you end up putting more and more and more packets until you've run out of memory, and you still have to deal with that case because that particular connection isn't working, but the other connections are working fine. You don't want the relay to reboot. You don't want the switch to say, "Oh my gosh, that one port isn't working right, and therefore I have to reboot the whole thing." Um, there are guarantees. You can provide connection guarantees. The circuit switch network is what we traditionally think of the old school wired phone network. It really turns out that there's not a huge amount of difference. So this is coming from somebody who worked on ATM decades ago, where the point of ATM was that they wanted to be able to provide circuit switch reliability over a packet switch network. So the way they did that was they used fixed size packets, 48 bytes, very small packets. The benefit of a 48 byte packet was that it could very quickly be switched. You literally could easily start processing the packet. This is great. You'd start processing the packet, sending it on the output port before it had finished coming in the input port. Pretty cool. And it was very, very fast. And it's still in use today. It's just not used at the home. It's not used in businesses. It's used in the backbone. Uh, And so there's less difference between circuit and switch and packet switch than you might think. We can build reliable network connections like circuit switched over packet switch networks. And we started by putting packet switch networks over circuit switch, so not a problem. All right, so what we focus on, in fact, in modern networking is what we call the end-to-end principle. And in the end-to-end principle, we choose to place the functionality where it's most appropriate. So we either put it either in the network, and we try not to mix the two. That's an important point here. Either it goes in the network or it goes on the endpoints. It's a principle. It's not a requirement. There's no hard and fast rule here, which is going to make this harder to deal with because you're going to get out in the real world and you're going to say, wait a minute, they taught us this idea that we should, keep everything in one place or the other. And it's like, yeah, that's a great idea, except when it's not. If you do have to implement functions end to end anyway, like encryption, encrypt on one host, decrypt on the other, don't do it in the network. You don't need to decrypt it on every single hop. What you want to do is you want to encrypt it on the endpoint. I spent many years working on transparent file encryption on the Windows platform. And one of the things that I was very proud about in that work is that we actually were able to keep things encrypted even if it was going to a network-based service. So for example, you run your Dropbox on your machine, and the file would literally be encrypted when it was stored on the disk on your machine. When Dropbox asked for it because it needed to send it up to the cloud, we would give it an encrypted copy. And so what got stored at Dropbox was encrypted. And then when you download it to another machine, we decrypt it on the endpoint. So we kept the keys only on the endpoint. We didn't ever keep the data in a decrypted form at rest. And turns out that Microsoft's own file sharing solution, server message block, was always implemented to decrypt the data before it sent it over the network, which left me scratching my head. Why would I want to do that? I don't want to trust the network. I want me to maintain the keys. I want me to own those keys. There's no reason the server should be looking in my data. It didn't need those keys. So the time that we'll actually blur these lines or violate this principle is because it's important for performance. Notice I said compelling. It can't just be because it's 0.1% faster. That's not gonna fly. There's a huge cost to doing this. We pay that cost because the performance benefit is large. So here's a simple case. We send a file over the internet. What we do is we break it up into smaller chunks, call them packets, segmentation, and reassembly. That breaking it up into chunks can happen at multiple levels. And I mentioned that before. If IP needs to, it will fragment. And IP does fragmentation and reassembly on the other end. We acknowledge receipt. You can do multiples at once. TCP doesn't send an acknowledgement back for each one. Instead, what it has is a protocol that says, if I send you an acknowledgement back for packet 479, that means I'm acknowledging all the packets before that too. So if I don't get packet number 464, I can't send an acknowledgement for 479. Instead, what I have to do is I have to say, yo, I didn't get 464. You need to send it again. And we work on these protocols because we could say I have received 470 through 479. I don't have 469. That's up to the protocol, and that's an optimization case. In fact, what actually happens is that we track pieces of the files received, and we acknowledge the pieces that we have received, and or we request the pieces that are missing. Think of BitTorrent. I think BitTorrent is a better example of a protocol where this makes sense. BitTorrent really does say, okay, I've received these chunks, but I'm looking for these other chunks. And it doesn't even necessarily get them from the same location. It can potentially get them from a multitude of different locations, and that provides us with a performance benefit because now we have better parallelism. Service types, we have datagram, which is best effort. As I described, that's like ordering something from AliExpress. May show up, may not show up. It's super fast. It's very simple, and it's super fast because there's no complexity to it, right? Go look at the UDP packet header. It's tiny. It's literally a port number and I think it's just an offset. because it knows what the length is, because that it gets delivered that way back from the IP layer. Um, so it's super, super simple. Tiny little header, doesn't have a lot of overhead, very quick and easy to process. Uh, if you need additional service guarantees, then you can add them at higher levels. And that is, in fact, what UDP is primarily used for. I mean, they call it the user datagram protocol. And originally it was because then you could build, it was a very thin veneer on top of IP, and you could build services in user mode using UDP packets. But in fact, UDP is implemented in kernel mode, and there are lots of protocols that use it. You can build it in user mode. Nothing prevents any of that. There's nothing magic about kernel mode software in that regard. It's very flexible, and it does scale well because we don't have the same state management issue in UDP that we have in in TCP. Of course, as I build layers above that, they do. They have to maintain and manage that state. There are no quality of services required, but physical networks do actually provide a quality of service guarantee. On your local network segment, they actually guarantee that your message will get delivered, assuming that the copper doesn't melt down or something. If you really need QoS, then in theory you can implement that at higher levels, but the reality is you need to have at least some level of guarantee from the lower levels, otherwise you're not going to be able to get that. There was a really good question for me after the class, and I'm going to mention it here, and that was, what does QoS mean? And so the idea is that there is some level of service that I have to have for this application. And the classic example that I always pull out, and there are others, but this is my classic example, is things that must be delivered isochronously. So, for example, Twitch delivers both audio and video streams to you. Those streams can be completely independent of each other, and sometimes they are. It depends on the protocol, but it's not uncommon for us to have isochronous protocols like this, where we have to have these two separate streams of data arrive and be processed at about the same time. A little bit there. If you've ever seen a video where the audio doesn't sync up, that's because it's not meeting whatever its quality of service was, because the two are out of sync with each other. And so that's a nice concrete example of one kind of quality of service you could potentially implement. And those services for that are isochronous services. So UDP is similar to the postal mail system, where you send something. It has a high probability of being delivered, but it's not guaranteed. It's not necessarily guaranteed to arrive in order. And if you're building on top of UDP, you have to deal with that. You have to deal with the harsh reality that the internet doesn't guarantee the ordering. You have to do it. So you have to grab things and then put them back in the right order. This is the analogy that I used earlier about, I'm moving a house from point A to point B. I need to label all the pieces when I start with it, and then when I get them to the other end, now I know how to put them all back together again. Datagrams are completely independent packets. But you have to put an address on each of those packets, so there is there's some potential overhead there. Although the reality is you have to do the same thing with TCP anyhow, because it always has the IP address. The IP address is actually how we know what machine to deliver it to, and the port number has to be there for TCP as well. There's always state in the TCP header, so TCP headers are still bigger than UDP headers. TCP, on the other hand, is a much higher service level guarantee protocol. It provides us with reliability guarantees. It guarantees in order delivery of the bytes. So UDP doesn't guarantee that. UDP just says, here's a packet, here's another packet, here's another packet. And if you want them in a particular order, you're the one who has to actually put that ordering information in your own protocol header. It's connection oriented. And there is a setup of the connection state, and then we have a teardown of the connection state. The data transfer occurs after the setup. So maybe the simplest answer is just use TCP, since TCP guarantees are greater than UDP guarantees. And of course, I had to get a once upon a time reference in here. All magic comes with a price. In this case, the price is connection setup's not free. I already told you about the HTTP 0.9 to 1.1 decision not to close the connection, and that was because it was so expensive to reestablish that connection. The three-way handshake, they call it. Hi, I want to connect. Okay, great. It actually sends 3 messages back and forth. And then you have a connection, and now you can actually send data. And at a minimum, the connection setup is 1 round trip, because as the sender, I don't have to wait until there's no acknowledgement to the second packet. It's just acknowledging the acknowledgement, and then you send the data. If you lose a packet, there's at least 1 extra round trip just to be able to say, I don't have this. Can you send it to me again? So there's a cost associated with this. There is a cost associated with putting the delivery order back together, because now I have to buffer things. I can't deliver it to the application because the application's guarantee is it will get the data in the right order. Won't necessarily get it in the same size chunk that it was sent in, but it will at least get it in the right byte order. So I have to track these things. I have to store things in memory. Sometimes TCP is just the wrong protocol. And the classic example, and this was Charton's observation from years ago, which was, if I ask you what time it is and you lose the packet, a reliable data transport protocol will guarantee that you'll still give me the time that it was when you first sent it. I don't want to know what the time was when you first sent it. I want to know what the time is now. And if you might not have necessarily thought about that, but that is actually the point, is that, oh yeah, there are some questions that really are topic based. They're what we call idempotent. So they don't require reliable delivery. And in fact, I like the time example because it's a really clear example of, you're right. If I ask you what time it is and you don't tell me, and then I say, I'm sorry, did you tell me the time? And you say, oh no, but it's 1:42. And you go, okay, is that the time now, or is that the time when you first looked? Oh, that's the time I first looked. That's not useful. It's not what I want. Okay, so the reality here is you want to pick the right tool. My ex-wife said that, and she was her family came from Sweden, and she said that all you really needed was a clog and a butter knife. And my observation is that if what you actually have is a chisel and a ball peen hammer, it might actually be the right tool if what you're doing is chiseling out metal. Butter knife is going to bend, the clog is going to, I don't know, confuse something. But that's my point. Pick the right tool for the job. There is no universal one right tool in this business, and this is part of what makes it difficult. We want simple answers, and almost always, especially in software engineering and building these real systems, it's a series of complex dynamic trade-offs. And sometimes we don't fully appreciate or understand those trade-offs when we first start designing it. So we start off with this what we think is a beautiful, elegant design, and then we realize that, oh gosh, that's not um, that isn't working out the way I expected it to. So I probably should rethink that. It's kind of like HTTP. So the HTTP protocol has traditionally been on top of TCP, and now here we are. We're moving it to UDP because it turns out that we're spending an awful lot of resources using TCP to maintain all of that state and ordering and whatnot, when we end up doing it all over again at the HTTP level. So maybe we're better off with UDP, and we can still do flow control. We just have to do it at the HTTP level rather than at the TCP level. So the common interface for talking to networks is based on the University of California, Berkeley, UC Berkeley, socket interface, or BSD sockets, Berkeley Software Distribution, the version of Unix that first described this. And there's a standard interface here. It is available on pretty much all operating systems you're ever going to work on. It is supported by Windows, it's supported by Mac OS 10, it is supported by Linux, it is supported by Unix. It's been ported to lots of other more esoteric operating systems because it's just a really good model for interacting with the network. Having said that, I will note that this model is largely driven by the way that TCP works. So the reason everybody ends up using it is because it fits the way that TCP functions, and we're talking TCP over networks. When it's UDP, it a lot of the stuff isn't there. You just open a socket and you just start listening to it, and you just grab packets as they come in, or you open a socket and you just start sending packets. A UDP connection is way simpler to set up and establish because it doesn't have the state. The reason that we have this whole interface is because of the statefulness of the interface. So here's an interesting question, and this is an implementation issue, which is what do we do if an application writes to a socket way faster than the network can send the data? Happens all the time. It's the quintessential leaky bucket algorithm. I have a hole in the bucket at the bottom where the data drips out to the network, and I have a fire hose at the top where I can stream data very quickly. How do I prevent the bucket from overflowing? And the answer is you shut it off. When you get to the limit, when your buffers are full, sorry, bucket's full, you just completely shut it off and you wait for it to drain. And the OS actually does this. It blocks threads. And, and when it's admission control. And when there's no more space, we block you. And when the space comes back, we let you continue. And this happens throughout operating systems. It's not unique to TCP. It happens in file systems as well because you can write data to a storage device much faster than you can write data to the storage. So you can write an application that pulls data or even just generates random garbage in memory and sends that to the storage, and it will go much faster than the storage itself can actually write it out. Datagrams, there's no blocking. There's no buffers or space issue. We just drop things on the floor if there's no space. And like, I don't know, something bad happened. It might return an error. In fact, most implementations will return an error if there's a problem with the underlying network. But if with the datagram protocol, we don't have to maintain much state. We don't have to track anything. You give us a datagram, we just slap it on the network, and we go, yeah, okay, it's on its way. So we can still run out of space because, like, that was the write example. On the read example, if I stop reading and the data still keeps coming in, then of course my host is buffering this data. So there are limits to that. So our brief architecture summary here: we have packet switch datagram networks, of which IP is the most common. We don't generally have network level state. It's all end to end, except when someone can justify it. We have lots of protocols that we can send data over, whether it's a satellite connection or an Ethernet connection or an asynchronous transfer mode connection. And we have transport protocols, which there's not a lot. And then we have lots and lots of application level protocols and different session layers and different presentation layers and so on and so forth. So the real lesson here is keep it simple, stupid. The KISS principle. Keep the network dumb. IP provides that minimum functionality. Just don't pay any attention to IPsec. Don't pay any attention to IP multicast, which aren't quite as simple. I mean, IP multicast has an entire protocol just for dealing with group membership, for instance, and that's state. So we bend those rules when we find that it's justified or useful. IP multicast is an interesting example because, as cool as I always thought it is, and that's probably because I was young and impressionable at the time that I was helping Steve Deering with some of that. I mean, Steve was doing the IP multicast work. I was doing the VMTP work that ran on top of IP multicast and whatnot. But We don't use IP multicast for much, unfortunately. It's a protocol that's always supported because it's all standardized, but it's not a protocol that seems to get a lot of use. Uh, we end up with smart endpoints where at the transport layer, like in TCP, we have flow control, error control, congestion control. Um, RPC can run on top of TCP or UDP. A lot of times it's better to run it on top of UDP because RPC ends up providing all of the services that TCP provides anyway. So you're paying the cost of TCP, and then you're actually still paying for the cost of all the services that our RPC will provide on top of UDP. And both ONC RPC and DCE RPC run on top of TCP or UDP. I always have. A big reason that you end up using RPC is because RPC goes beyond what TCP does in providing authentication and security protocols. Uh, DCE RPC certainly does. Less so ONC RPC. You end up doing it as a layer on top of that. Session management and additional reliability. So if you're running RPC on top of UDP, you're not even basically, you get the same kinds of guarantees for reliability that you get with TCP. Things are kept in order, so on and so forth. And so there you go. That is the remainder of the discussion about networks. And I went into probably more detail than I would have if I had gone through it next Tuesday. Um, so hopefully you found that useful. And I will see you uh, next Tuesday for the next lecture. And thanks for not watching. I have no idea if anybody's watching it, to be honest. So we're done.